I walk into a room and people have concerns about the reservoir, they usually ask one of three questions. How long do we have before there's an impact? Can we extend that time? Is there anything we can do about it? And if not, what are the potential implications of taking this dam out? If you need to take the dam out, there is sediment behind those dams, and what's the fate of that? And so that turns into the three types of models that we do with sediment transport models in reservoirs. We do life cycle models for the reservoir. We do sustainability models, things like flushing and sluicing, how will those affect the reservoirs? And then we do dam removal models. At HEC, I've applied RAS multiple times to each of these questions, and we supported many others who have done that. But I'm just going to show you one of each because it kind of shows you the sorts of analyses that you can use to apply a model to these questions.
Hello and welcome to today's webinar on reservoir sedimentation and dam removal. We've titled it, What's Mud Got to Do With It? That's a nod to the late, great Tina Turner there, but I'm your host, Cray Price with the International Water Training Institute. And on behalf of the Australian Water School, we wanted to thank you all for your attendance today from all around the world. It's a great turnout from almost 100 countries. Now let's introduce today's speakers. If you can turn on your cameras, Marty Stanford, and let's start maybe with Marty, if you can introduce yourself.
Sure, thanks, Craig. Hi, everyone. My name is Marty Teal. I'm president of West Consultants, and WEST is actually an acronym. It stands for Water, Environmental, Sedimentation, and Technology. So sedimentation plays a big part in what we do. We're water resources engineer consultants, and we do work all over the world. And I've had a lot of experience in modeling over 30 plus years. And I'm happy to be back again with the Australian Water School to participate in this webinar with my good buddies, Craig and Stanford.
Excellent. Stanford's been with us before as well. One of the things we'll be highlighting today is the River Mechanics podcast, which is exciting. Talking about acronyms, RSM. Let's hear what RSM stands for. And then Stanford, you can just tell us a little bit about your background and where you're coming to us from today.
Hey, Craig. Yeah, RSM is Regional Sediment Management. It's one of the things that the Corps of Engineers thinks about, and I work for the Corps of Engineers. I'm at the Hydrologic Engineering Center. I'm on the RAS team. I was involved in the release in the last 24 hours, and I'm in charge of the sediment transport capabilities in HEC-RAS.
All right. Well, what we can do now, maybe we'll pull up the poll results and see what everybody's background is here. First of all, as normal, we have most people from commercial and consulting, but we do have quite a few from government. That's a bigger turnout from government than we typically have on these webinars. And looking at the software, quite a few HEC-RAS users, but we also then wanted to check out SRH2D, which we'll hear about a little bit today as well. And it's good to see that, if those numbers are low, we want to see if we can make a plug for anybody wanting to learn that as well. And we'll cover some of those resources in the end. Now, this is probably the most important question. Number 3, have you been involved in any of these? No, it looks like most people have not been involved in dam removal or reservoir sedimentation, in terms of the sustainability or the life cycle analyses. And so what we want to do is make sure we introduce this topic to you because it's tremendously important when we're getting into reservoirs and dams. Let's have a look at some background resources because in a short presentation, we don't necessarily have a lot of time to get into the full details of it, but we want to make sure that we arm you and provide you with all of the resources that you need to get moving along in this topic. And if you want to model it, we'll give you those resources as well. So reservoir sedimentation and dam removal, I've set this website up at hydroschool.org/mud in honor of today's title, What's Mud Got to Do With It? Here's a photo of the Nolichucky Dam, which I'll talk about briefly today as well, which even though you see water there, it is fully silted in. Almost, I think 99% of the volume is taken up by sediment. Last month, we had Grady Hillhouse come on from the Practical Engineering channel and show us a couple of videos that are very relevant to today's discussion as well. Here is a link to Stanford's River Mechanics podcast, and we also have some training courses. What we'll talk about today has a lot to do with how water moves dirt, and if you want the basics of that, we've got some courses in fluvial geomorphology. Marty teaches a course here in sediment transport. If you want to do numerical modeling, we've got that as well. There are some additional webinars and video clips that Stanford has provided here from his channel, and along with some others about the basic principles that underlie some of the things we'll talk about today. We also have a few additional resources here, some papers that Stanford and Marty have provided, and we'll continue to add to this list based on your feedback today. And if you are interested in going any further with it, as Stanford mentioned, the new version of HEC-RAS 6.4 was just released 24 hours ago, and we'll hear a little bit about some of the functionality in that software that will help you with some of the reservoir sedimentation analyses. We also have then, again, as we mentioned, the Fluvial Geomorphology Essentials course that's available on demand, along with Marty's course here on sediment transport, and some additional background principles in our training series that covers all of the principles that we thought was fundamental for running numerical models in hydrology and hydraulics. Now, I'll just briefly start with a couple of video clips that Grady Hillhouse had provided to us last time around when he came on with us live. And I'll show you here just the overall concept that we've got that we're be talking about today. And that's that, you know, an obstruction in a river system will block the sediment. So I can go back and forth through this, and you can have a look at some of the stream tables that they use to set up some of these additional models. I'll show you some of the ones here in fast speed. It's already in fast speed, but I'm going to speed it up even further and just show, you know, again, if you picture this as one of these glory hole spillways in a reservoir, picture this as a dam. You know, we've got deltas forming, we've got sediment coming in that can't go out. There are all sorts of issues around reservoir sedimentation that sometimes don't get thought about. And I guess the overall principle that I wanted to hit before we turn over to Marty is that when you put in, say, a cubic meter or a cubic yard of concrete for a dam, every year, in some cases, that amounts to 10, 15, 20 or more cubic meters or cubic yards of sediment that's going to accumulate behind that dam, depending on your system. And so when we do our cost cycle analysis on, you know, the value of putting in one of these structures and not account for the life cycle cost of what it takes to manage the sediment behind it, we're sometimes left with a problem, in this case, where the solutions to that problem are 100 times what the cost of the dam ever was. And if we were to consider the full life cycle of these things, a lot of these would not have ever been built in the first place. Now, let's go ahead and have Marty start sharing your screen. Keep the questions coming in the background from the audience. Again, upvote those that you want to see addressed in the live panel discussion, and we'll go ahead and have those addressed later on. So Marty, if you can start sharing your screen, and then we'll have Stanford come on. And Stanford's going to be answering your questions in the background. So to have Stanford on, it's a great privilege for us to have Stanford on. And so if you can keep him busy with some questions in the background, and then vice versa, when Stanford comes on, let's keep Marty busy with some questions, and we'll make sure that we keep this interactive. So over to you, Marty. I can see your screen just fine.
Thanks, everyone. I'm going to present two case studies, just some stuff that we did involving modeling of reservoirs. The first one I'm going to talk about here, so work we did for TVA on one of their dams called Nolichucky. And this is an older dam built in 1913. It's like Matilaha that Cray showed. It's completely filled with sediment. It's basically all the water just goes over the top, as you can see in the picture. It does have one gate. The powerhouse is actually decommissioned, but it's still there. You know, they haven't removed the dam, so there are dam safety issues. And so one of the things that TVA had to do was to replace the gate that was there. And the big question was, what was going to happen with the impounded sediment when they removed that gate? Was it going to cause a high concentration flow to go downstream or not? They had to know this in order to do their environmental permitting ahead of time. And so they were kind of worried about several things. So the questions we wanted to answer were, what kind of maximum concentrations would they have and for how long? You know, can we predict those concentrations and compare them against the kinds of concentrations that would happen during natural high flows? And then finally, kind of the big one for them, because it involves a lot of dollars, is could they avoid having to dredge in the reservoir ahead of this maintenance on the gate? Okay, so there's just another picture, all the flow going over the reservoir, the gate's kind of on the left side of the photos there, and all the deposits are in the reservoir. For this particular study, we used SRH2D, which some of you, based on the poll, are familiar with. It uses the 2D depth average St. Bernard equations. It's a couple non-equilibrium sediment transport. We've used this model with good success a number of times. Of course, bathymetry was one of the inputs that we needed. We actually created two different computational meshes, one with the gate closed, which is on the left, and one with the gate open, which is on the right. And we ran our simulations on that to kind of get the range of concentrations that we might expect. We had samples that were taken of the material in the bed at different locations. And from that, we were able to develop layers of different types of sediment. In this case, the picture I'm showing is kind of broad groupings of sandy, silty, and so forth. Boundary conditions, we looked at a couple inflows. One was a very low, for this system, inflow of about 54 cubic meters per second, which corresponds to conditions under which they anticipated doing the gate replacement. And then we also ran a higher flow, about 370 cubic meters per second, which corresponds to about a yearly recurrence flow. Okay, we had some other 1D modeling results downstream, so we're able to use that for our downstream boundary conditions. And we developed roughness. And one thing I do want to point out is with SRH2D, you're able to develop subsurface models. So if there are changes in gradation, say, of your material with depth, you can do that. So we looked at a couple different scenarios. First two were with the gate closed, one with that very low flow, one with the approximately yearly flow. And then we did a couple simulations with the gate open. One of the problems we had that there was kind of a gap in the surveyed bathymetry just in front of the gate because it was hard to get in there and collect the data. So we made some assumptions and about the whether it would be actually a hole there or if it was actually filled in with sediment. So we actually ran it both ways. And we looked at the results here showing this is just depths, and you can see that there's an area where it looks like it's a deep hole, but it's actually a lack of data in there. And so this is just showing a profile view, some water source profiles with the gate closed and the gate open, both with flat bathymetry, which is basically filling in this hole, and that it would be straight across, and the other one with the bathymetry that we were provided. Okay, so I'm skipping straight to some of the results here. This is looking at shear stress. I'm going to focus more, and I apologize that a lot of this is in English units, but looking at the shear stress, at the concentrations is really what I want to get to. So this is showing that for the simulations that we did, for the high flow with the gate closed, the concentrations were much higher than all the other simulations. Okay, and if we kind of look at what we were getting with the gate open with the survey bathymetry, again, it was pretty low, about 100. So what we found based on, I should say also on the scour, it was very small, really 60 centimeters, only about less than 10 cubic meters. So again, pretty small. Maximum concentration was also pretty small. Showing these results, just flashing it up there really quickly. What we found, I'll skip the conclusions here, is that for the anticipated flows during construction, even with the gate out, the concentrations were very low compared to what was already coming over the dam during an approximate yearly event. Okay, and that factored into their environmental analysis. They avoided having to do any dredging in the reservoir and were able to save some money. And this is just after we did our work, they were able to go in and install the new gates. They had a environmental finding of no significant impact, so that really smoothed the way. I'm going to very quickly present the second case study here, and this one was using HEC-RAS, although 1D HEC-RAS, not 2D. This was some work that we did on the lower Susquehanna River in the eastern United States. This is just the location map where it's on the eastern seaboard. Susquehanna River feeds into Chesapeake Bay. There's been a lot of previous studies on that. Some of them actually used HEC-RAS, but none of them had used the true unsteady flow in HEC-RAS. This is what we did here. So instead of using a series of steady flow pulses, we're actually able to do true unsteady flow, and that way we're able to conserve volume, which is especially important in reservoir systems. And I'm sure Stanford could talk a lot more about that. This had both cohesive and non-cohesive sediment. Here's our reach, bunch of cross sections is pretty typical. We had two boundary conditions, one that was interior boundary condition, where there was a series of gates at one dam, and then our downstream boundary was another dam. Our motivation for doing this is that there's a third dam even further downstream called Conowingo Reservoir, which is significant in terms of trapping sediment going into Chesapeake Bay. So I'm skipping through this very quickly, but we did hydraulic model calibration. I'm sure Stanford would be happy to hear me say this, but as he said many times, and we both heard from Tony Thomas, you really can't have a good sediment transport model until you know you have the hydraulics correct, right. And so here's a calibration that we did as part of the modeling. We actually, based on the collected data we had for calibration, we had a bunch of different ranges within these reservoirs. And we had one period that we used for calibration and another period for verification, where we compared the model results to what was measured based on the field data. And so in this case, we didn't have exact numbers. We had a range of potential changes that were observed in the reservoir. And then we had our model results here. And so this is showing a mass change. Here's a bed volume change. Again, apologies, this is in cubic feet, not cubic meters. But you can see that at least for the validation period, calibration period, and then validation period down below, we were within the range of what was measured. So we felt pretty good about that. And we were able to develop sediment rating curves at different locations within the reservoir that would then feed in to a three-dimensional model, which we were not doing, but we needed to create the boundary conditions for that for the Conowingo model downstream. So I think I'm right on time, Stanford, to leave you enough time here. I blew through that, but I'm happy to answer questions at the end if there are any on these two case studies. So Cray, I'll hand it back to you.
All right, yeah, and Stanford, if you can start sharing your screen already. Yes, Marty, quite a few questions have come in about these case studies. So if you want to have a look at those, I think we've, Stanford and I have both deferred those to you. So have a look at those in the chat line in the background, and we'll address some of them live when you come back on. Stanford, I can see your screen just fine. Your video's coming up as well.
All right, thanks, Marty and Cray. So I'm Stanford Gibson. I'm the sediment transport specialist at HEC, also one of the national sediment specialists of the Corps of Engineers. And I'm going to talk a little bit about how we use RAS, which can be used like any other sediment transport model to do life cycle analysis for reservoirs, sustainability analysis, and dam removal analysis. Because when I walk into a room and people are having trouble with their reservoir, have concerns about the reservoir, they usually ask one of three questions. How long do we have before there's an impact? Can we extend that time? Is there anything we can do about it? And if not, what are the potential implications of taking this dam out? I saw a question in the chat, a lot of concern on the Klamath about the downstream impacts of dam removal. I know the teams are doing a lot of great science on that, but that's a big question that comes up. If you need to take the dam out, there is sediment behind those dams, and what's the fate of that? And so that turns into the three types of models that we do with sediment transport models in reservoirs. We do life cycle models for the reservoir. We do sustainability models, things like flushing and sluicing, how will those affect the reservoirs, and then we do dam removal models. And so, we've at HEC, I've applied RAS multiple times to each of these questions, and we supported many others who have done that. But I'm just going to show you one of each because it kind of shows you the sorts of analyses that you can use to apply a model to these questions. And so the first topic is reservoir life cycle modeling. And the life cycle modeling is just, how long do we have until there's an impact? I just recorded a podcast with John Shelley today about reservoir sedimentation modeling, and he says, we talk a lot about how the vulnerability of our dams and very low probability of dam failure. But every reservoir has a 100% chance of failure on a long enough time scale because of reservoir sedimentation. And so we have to ask the question, what is that time scale and when will those impacts come down the road? And I think the most interesting study I did is really one of the first ones I did is on the Arghandab Reservoir. The Arghandab Reservoir is upstream of the Arghandab Valley, which is a thin riparian corridor of subsistence farming in Afghanistan, and they're completely dependent on the water from this reservoir. The reservoir supplies all of the water for the downstream subsistence farming, and if it was to fail to supply that water, say because of a multi-year drought, then it would be a humanitarian disaster because the entire region depends on this water. The problem is that this is the watershed associated with the Arghandab Reservoir. These are the badlands of the Hindu Kush Mountains, and the sediment loads are outrageous. When I first started this work, I'd only really worked in North America and Southeast Asia and a little bit in South America, and I'd never seen these kinds of sediment loads. And so the Arghandab Reservoir is about a third full of sediment, and the more the reservoir fills with sediment, the higher the risk that a multi-year drought won't be able to supply downstream users. And so the question is, how many years of deposition can we sustain before the risks of supplying downstream water become unacceptable? And so we had repeated cross sections. This is, like Marty said, and like one of the people in the Q&A said, with sediment modeling, if you're coming to sediment modeling from hydraulic modeling, of course you're supposed to calibrate a hydraulic model, but hydraulic models are forgiving. Sediment models are not. You absolutely have to calibrate a sediment model if you're going to trust the results. And so we had these cross sections from when the reservoir was closed and cross sections about 30 years later. And so we could calibrate this model and then use that calibrated model to project into the future. And so we built a RAS model, a very simple RAS model. I actually use this for our workshops because you can run 50 years in this model in about 2 minutes. And so it's really, really powerful. You can do lots of different life cycle analyses, games, and then you can, the boundary conditions for a sediment model is like you need flows, but then the flows also need sediment. And so we had this flow load rating curve, a very sparse, but actually gave us what we needed in order to calibrate the model. And so then when you calibrate a sediment model, there's lots of things you can calibrate to, but like Marty showed, the best thing to calibrate to is volume change. And so you can see here is that we've got the water surface elevation of the pool, but then we have a series of bed elevations. The big thing with sediment models is that we call them mobile bed. We like to call the rest of hydraulic modeling, blue water fixed bed modeling, which is really pretty easy in comparison. Mobile bed modeling, you have two free surfaces. The water surface changes, but also the bed surface changes in response to the sediment flux and deposition. And so you can see every 7 years is what I'm plotting here, the prograding delta. And so then we compared it to the actual volume change at each of these cross sections. And so you can see the computed volume change and the measured volume change. We didn't have to change the loads much to do this, but we did have to play around with the sediment gradations of the flux coming in because we didn't have much information on that. And so that became our primary calibration tool. And once we had the model calibrated, then we could project into the future and make some assessments about what is the potential timeline of catastrophic outcomes and what are some of the things that we could do about it. But let's actually switch over to the second question people ask is, okay, if my reservoir life cycle model tells me bad news, is there anything we can do about it? Can we extend the life cycle of this reservoir? And the main thing that people want to talk about in these models, there are 6 to 8 different reservoir sustainability management options that you have on the table, but a lot of people want to first look at, well, can we flush sediment from the reservoir? And so there's a number of reservoir flushing models that we've done in RAS. I'm just going to show you one of them. This one on the left, Spencer Dam. So Spencer Dam is on the Niobrara River, which is a tributary to the Missouri River in the northern United States. And if we zoom in on the Niobrara Reservoir here, you can see that this thing looks pretty full of sediment. This all used to be blue water, well past this picture. And so in 1925, apologies for the acre feet. An acre is about a soccer field, and a foot is 1/3 of a meter on top of it. And so in 1925, there were about 10,000 acre feet. By 1949, there were 35. And that's because this watershed drains what we call the sand hills of Nebraska. The sand hills of Nebraska are exactly what they sound like. They're sand hills. And so this reservoir filled with sand in less than 25 years. And so in the 1950s, they retrofit this dam for flushing gates. And then over the course of the next 50 years, they flushed the sediment out of here twice a year in order to just get enough space to generate hydropower. Well, this got grandfathered in with permits, and so it became a laboratory for the Corps of Engineers to test our models against, because we could go in and we could make measurements and see how the models do in these pretty chaotic systems. And so this is a flush that happened in 2016. This is about an hour into the flush. This is about 4 hours into the flush. You can see we're already creating multiple channels. You've got these terraces forming. And this is about 8 hours into the flush. Now we've got deep channels forming. We're going to put some videos up on this at some point. And downstream, here you have the Missouri River flowing to the right. And then this is the sediment pulse just 1 day later from the Niobrara coming into the Missouri River. And so we went out and we took, just like with Arghandab, we want before and after cross sections because we want to do a volume calibration. But we also, we used the before cross sections to build our RAS model. We actually built a structure here because we want to operate the structure. One of the things that we're interested in is how the different structure operations could affect the flush, and can we change the concentration pulse that goes downstream. And so, with the reservoir life cycle model, you're mainly interested in what is the sediment flux coming in, because you're interested in deposition. For a flushing or a dam removal model, you're not as interested in the sediment flux because everything happens so fast. That's not a big deal. The more important thing is the gradation of the sediment on the bed. And so we went out and we collected these bed gradations that we put into the model, so the model would know what kind of material it's eroding through. And it sure looks like you would need a boat to do that, but you do not. This reservoir is completely full of sediment. That is my colleague, Dr. Boyd, out there collecting sediment samples in the middle of the reservoir. And then the other thing that we had, we calibrated to volume change, just like we have in the other model, but we also had concentration downstream. And so the U.S. Geological Survey made concentration measurements downstream while we flushed this dam. So again, we could test the model. And so we calibrated the model to volume change, but the thing I want to show you is the concentration downstream. And so here we have the observed concentration in diamonds, and then the measured concentration, and then the computed concentration time series from the model downstream at that bridge. And so we have some confidence that we are reproducing the result downstream. And so the main thing that we wanted to ask is, could we operate the dam differently in order to change the concentration downstream? Because that's the main thing that people care about, is what is the the sediment concentration, what is that moves downstream? Is that going to affect down stormwater or wastewater treatment, drinking water intakes, ecosystems, and ecological communities? And so then we started gaming the model to see, could we flush the same amount of sediment, but over a longer period of time and avoiding the peak concentration? And so you could do that manually, but one of the nice things about unsteady flow and RAS is that we have these operational rules. And so we added sediment triggers to the operational rules. And if you haven't used operational rules in RAS, I have a video on this. I have to tell you that operational rules sound scary, but they're the most powerful thing that you'll ever discover in RAS. So give yourself an afternoon, watch the video, try something out, and you'll have a new tool in your tool belt. And what you can see is we set up these operational rules so that if the downstream concentration exceeds 30,000 milligrams per liter, then we close the gates. We set the gates to 0. And otherwise, we open the gates. And so what you can see over here on the right is the original concentration time series, the calibrated one. But then this is the time series with these operational rules. And you see it rises to about 30,000 milligrams per liter, and then it hangs there until it falls. And so we pass the same amount of sediment, but we pass it over a longer period of time, and we avoid that really high peak of 50,000 milligrams per liter. Which brings us to the last thing that people will ask you to do with the model and reservoirs, and that's a dam removal model. And dam removal models, basically we've gone beyond where flushing will help, or often it's really just the liability or the ecosystem impact that people are looking at that said, the dam might not be full of sediment, but it might have outlived its welcome. And so people want to take it out, but there's usually, 10 to 50 years of sediment behind that dam, and you can't just take it out without asking the question, where's that sediment going to go and what are the impacts going to be downstream? And so, one dam removal that I was involved in is a dam removal they were considering in Springville in Western New York. And so we went out and we collected cores. The team went out and collected cores of the material in the reservoir because, again, the upstream flux isn't going to matter much. What matters is the 30 to 50 years of deposition. And so the local material, the gradation of the local material matters more. And so we got gradations of the local material, and Waleska Evacheria, who is Waleska Evacheria Doyle now, did a lot of this modeling, and I supported her as she used the model, the dam removal model. And what you can see here is the time series of erosion after the dam is taken out. And one of the things that we have in RAS is you can use the kind of classic veneer model that we use in 1D that kind of reduces the whole cross section at once. But we also have this simplified channel evolution model that forms a channel that goes down and out, more like a rapidly developing channel in a flush or a dam removal would do. And this is really helpful. But one of the problems with dam removals is that you can't calibrate them. They're novel events. And so we don't want to deliver a model that's uncalibrated. And so what we did here is, instead of delivering a model and saying, we didn't calibrate this, but it's right, we did sensitivity analysis. And so we didn't say that it's going to take, 38 days for the sediment to erode. What we'd said instead is it's going to take months, not days, or days, not hours, but also days, not years. And that's the way that you can constrain a uncalibrated dam removal model. But Chris Nygaard and I were involved in a dam removal model on the Snake River. And on the Snake River, the Corps of Engineers has 4 dams. And as part of the latest environmental impact statement, we were asked to analyze what it would take to remove these dams. And so one of the questions I get is, how do you model a dam removal in RAS? Well, you use a very large gate. We have these gates that are actually open air, and they open from the top down. And so if you put in a very large gate and have it closed and then open it, you can do a dam removal in the middle of simulation. You can open it 1 foot a year if you want to do, say, a staged removal. And so that's what we did. We put these dams in, and we calibrated them, and then we calibrated this model to deposition, and we looked at the deposition over the course of the decades that these dams have been in. But that's not a very useful calibration, because you want to calibrate not just in general, but to the process that you're going to be evaluating. And so in 1992, they actually drew down these dams, and so we calibrated both the bed change and concentration from the 1992 drawdown to give ourselves some confidence that we're simulating not just the model, but like the actual process that we're trying to capture. Oh, and Chris Nygaard and I talk about this model on the podcast if you're interested in that. And so this is noisy, but I love this plot. So I've got to show it. These are the results. And so you've got the flow, and we did these for a wet year scenario, dry year scenario, and medium year scenario to give a sense of the uncertainty. And what we're looking at here is the concentration time series downstream of a multi-stage dam removal, both by total concentration, but also by grain class, so that you can see that actually the fine material blows through in the first couple of years, and you get pretty high concentrations in the 160,000 tons per day. But after the first year, as it switches to sand, the concentrations fall quite a bit, and the fine sand moves its way through. And so you can use these results to determine, what are the peak concentrations downstream that ecosystems will encounter. How will the sand move through the system and affect flood risk downstream? How long will that flood risk challenge persist? And those sorts of things are the way that this model can be used. Right, and we have a paper on this if you want to follow that SEDHIDE link. And so the last thing that I'll say here is that Cray has mentioned this a couple times. I do have a podcast on river mechanics. The first season is out. It's the RSM River Mechanics podcast. It includes a conversation with Chris Nygaard on the Snake River dam removal model. But the reason I want to finish with this is that the second season, we're going to have a mini season, a 4-episode mini season on reservoir sedimentation. And so I've already recorded interviews with 2 of the top reservoir sedimentation thinkers out there, George Annandale and Greg Morris, who have written the 2 most popular books. You know, George's book is kind of a big policy thinking book, and then Greg's book, the Reservoir Sedimentation Handbook. If you're interested in this, he offers a free PDF version of this online. It is the resource for reservoir sedimentation. You want to go get that. But we have interviews with both those guys. I interviewed the 2 top thinkers in the Corps today. We're talking to Jennifer Bountree tomorrow, and the U.S. Bureau of Reclamation, who's put together really important information about dam removal. And I'm going to run those 4 episodes as a mini season towards the end of the summer. And so if you're interested in this topic, keep watching that feed because that'll come along.
Awesome. That's some great material there, Stanford. We love your energy and enthusiasm, and you'll see that come across in the podcast as well. Marty, if you want to turn your camera back on as well. I'm looking at some of these questions. Some of them get pretty intense. I think to give Stanford a chance to go through them on the text, let's start with Marty. And I think the first couple of questions that came up about your projects were about calibration. So you might want to say something about the importance of calibration and state whether or not the models that you presented were calibrated. And then you may want to take a look at some of those other ones that have been upvoted and how some of these how some other applications might be handled that might differ a bit from the case studies that we've seen. So maybe just start with the calibration question.
Sure, yeah, and I'll encourage Stanford also to look at the answered questions. I was typing in, trying to answer some of them, but he might have a different take on some of those, even though they're in the answered section. But I would say on the first one I presented on Nolichucky, we had some results from a 1D model that had been calibrated, and it's a very linear type reservoir for the most part. So we were able to calibrate, our water surface elevations and our N values to that. Unfortunately, we did not have detailed distributed velocity information, which I would have loved to have had for, our 2D to be able to compare, what we were getting for our model depth average velocities with some measurements out there. Unfortunately, we weren't able to get out there with our equipment, and that wasn't available from TVA, and we were on a timeline. So we did have some calibration. It probably was not as rigorous as I would have liked, but we were satisfied with, the pool. It went up for quite a ways, but it was relatively flat for a long distance also. And we were able to match the water surface elevations fairly closely. For the other case study on the Susquehanna River, I showed that we were able to reproduce water surface elevations at gauge locations pretty accurately, and so we were pretty happy with that also. Let's see. And there was a question, I guess, in the chat about Spencer, since Stanford brought it up, and yes, that dam did fail. And I was on the forensic team investigating that failure, and we did publish a report which is available through Association of State Dam Safety Officials, and we can post that link. In fact, I think Liberty had sent it to just the presenters. Let's see. There was a question about orientation of cross sections. I think that's something that's you guys go over in other courses also, but really should be perpendicular to the flow direction, which may or may not be the same as perpendicular to, the river itself, the axis of the river. So that's something that comes up a lot, especially if you have bends or other things going on, which are especially 2D and you're trying to model with a 1D model.
No, great. No, thanks for that. One of the one of the questions that came up that I thought I'd mention as well. Very unfortunate. What's I mean, we look at these things in terms of the physics and the politics that sometimes gets involved. I know when we did a dam breach webinar a while back, we talked about World War II and the dam busters, and some of the dams. What would it take to breach a dam? And there are times when the Corps of Engineers has used explosives and got some of their explosives experts, practicing on a permitted and approved dam removal, just to help out with that process. But yeah, very disturbing that a few people mentioned in the chat what happened yesterday. There's going to be some major impacts from the dam that was destroyed in Ukraine, and yeah, watch that very closely, because you can watch satellite data and see, this is a dam removal, an extreme dam removal in this case. But yeah, just something that I thought I'd mention. If you want to Google that and have a look, that data is still coming live and on the fly. Another video that you may want to just Google some of these things. You'll see these come up on, I don't know, Twitter or TikTok or whatever, because it's just watching what comes out of a out of a dam when you start sluicing sediment through is sometimes a bit of a when you watch as it starts spraying out here. I don't know why that gets a lot of hits, but some of these videos get a million hits just because people like to see the blockage unblocked. So with that, Stanford, if you want to take the most, maybe some of the most upvoted questions on your end, I see quite a few very high-tech questions that I wanted to kind of pass on, and maybe you wanted to give a stab to. So I'll let you select which one to hit next, but maybe we'll turn it over to you for that.
Well, it looks like the top upvoted one is about dissolved oxygen during a reservoir flush, and that's really important. That's one of the things that we're looking at all of our flushes. We were at a flush in Kansas, and just a little 2-hour pressure flush, not even less than an hour, and they're just flushing some of the silt from the gates. So it's not really sediment management, it's more like structure management. And there was this very small pool receiving that water downstream. And as the water came out, you could kind of smell it. And whenever you can smell it, that's anoxic organics. And as soon as that material hit the pool, about 30 Asian carp started jumping out of the water, and we think that that's in response to the drop in DO. And it's quite a sight. Those are big fish, and have 30 of them jumping out of the water in a little pool is quite a sight. And so the question is there anything you can do about it? Well, in the early flushes in Spencer, they had the same problem. Spencer is full of sand. There's a couple of things that cause the DO crash associated with the flush. One of it is you're just taking deep water. The deep water has low DO, and if you're flushing, you're probably taking deep water. And so if you can mix that with surface water somehow, if you have some sort of if you could use a siphon or have some sort of variable release, I think that's just going to help to begin with. But then one of the things, they ran into that early on in Spencer, and when Spencer started flushing, that was a different world where fish kills were tolerated, but they were having fish kills, and they wondered if there was anything they could do about it. And so what they did is they started with a pre-flush that just kind of put a low DO that put a low sediment load in that caused the DO to drop but not crash. And what that did is that actually encouraged the fish to find refuge, to move downstream, and then they did their flush, and that worked for decades. And so it's very system specific, but it's something we're looking very carefully at. We always monitor anytime the Corps does any sort of flush, drawdown flush, we always monitor DO downstream, and there's usually just a threshold that the DO can't, just like we saw with the concentration threshold, if the DO drops below a certain level, you stop.
Ah, sounds good. One question that we have, just again, given the fact that we've just had this new release that I think you've been working on for at least 6 or 8 months now, Stanford, this new release of HEC-RAS 6.4. Are there new tools available to us now? Would you still approach some of these models the same way, given the length of time that you want to model? Would you start putting these things into 2D? And do you see 3D modeling coming up, quickly enough to be able to help us out with these sorts of analyses?
So I'm
There we
showing
go.
my screen.
Here's your plug. Yes,
These are the new features in RAS, and so you can go and look through them. And a lot of these I put in there because a lot of them are sediment. The
That's what I
most
thought, yeah.
important thing is that you can now do a reference area in RAS, and a reference area is really what we needed for sediment transport, 2D sediment transport, because you can query a time series associated with a bunch of cells. And so that's one of the things that really helps move from 1D to 2D. We are doing more of this in 2D. And we also do, we have an intermediate level of complexity. We have what we call fixed bed 2D sediment transport analysis, where you're not actually changing the bed, you're just comparing the capacity. And that's not as useful for reservoir modeling, but for other sediment transport models, it can give you a sediment answer without doing a full-blown mobile bed model. So you can get probably 50% of the value in 10% of the time. So this is something we're doing a lot. And then if you're not familiar with the rating curve calculator and some of the tools that we have in order to compute your sediment load, we're teaching every time we teach a reservoir sedimentation class, we teach this sedimentation calculator. This is just the way we do business, and so I would recommend any of those to help with reservoir sedimentation.
Excellent, thanks. And with those release notes, if you are going to download the latest version, you will also see the training resources that are available from the Corps of Engineers. And if you want to try doing some of this yourself, the on-demand course that Marty taught, we do touch on 2D, and we'll talk a little bit more about, based on today's feedback, is this something that we want to see more of in terms of course offerings, and maybe we'll start applying the new features in sediment. Now, the new features in HEC-RAS 6.4 for 1D and 2D blue water modeling, as Stanford called it, are going to be held in a live course coming up, a live online course coming up in the next month or so. Have a look at the Australian Water Schools website if you want to sign up for that. Marty, any comments or
I did.
that you want to make on that
one? Since Kathy's question had the most upvotes here, I wanted to say, I know there's reservoirs here where they're doing a couple things to try to, help get more oxygen into the system. Stanford had mentioned some reservoirs will have towers where you can do selective releases from different levels. So you send some water from higher level, take some water from a lower level. They have not only different concentrations of oxygen, but also different temperatures, and depending on the fish species, that can be very important to get the right temperature downstream also. I know there's some dams where they've actually installed basically bubblers downstream of the dam to help improve the turbulence there from the releases and entrain oxygen right away. So there's other things people have been trying out. I'm not sure how effective they've been, especially with the sediments that she was mentioning there, because it's just really hard. If it's stuff that's been sitting on the bottom and doesn't have any oxygen with it. Another problem is, of course, organics. If there's organics that you're trying to do and they've taken up, all the oxygen, it's really hard to get more in there. So, I'm waiting for the organic sediment transport feature, Stanford.
Any and no promises there?
Oh yeah, I'll be version 8, right?
Yeah, excellent.
If someone shows me the science that we all trust, I'll put it in there.
There we go. So yeah, a couple of people have asked the questions about, well, so what do we do? And there is no good answer. If a dam's going to go in, whether it's a design dam or if there's a dam that has gone in, there are no quick fixes to this. I mean, you can, everything that you see here still has impacts. You'll have downstream spawning gravels that get covered up for a while, and that can cause impacts. Even if you do this sluicing, somebody asked the question, well, does that can that put it back to how it was? Well, no, because the energy that it takes to establish that head cut and put that profile back, that may just be along the river channel, and you'll still have everything along the embankments that's still up there that doesn't have sufficient energy as it would have with the natural pulsing. And so, full removal of defunct dams, it generally has to be done over an extended period of time, but that's pretty much what you would need to do. You can mechanically pull these things out. You can build pipelines and try to take these things out as a slurry. There are a number of ways that you can approach this, but again, the costs of moving that sediment, in that case study that I showed, I think we did an economic analysis on it, and it was over 100 times the cost of the dam. So these are things that need to be considered in the beginning, and we need to just make sure we predict in the end, as we're doing any dam designs for new dams, how long is the life of that dam, and should we be putting this in? And this is the same thing with mining pits and everything else. If the cost of cleaning up after your mess is more than the revenue that you're going to gain during the operational life, maybe some of these things ought not be built. So that's a kind of an answer to about 4 or 5 of the questions, or a commentary on about 4 or 5 of the questions.
Hey, I'd like to comment on that, because when they looked at removing the Elwha Dam up in Washington State in the U.S., the Bureau of Reclamation did a lot of that modeling, but they looked at trade-offs. So up there was salmon runs. There's different seasons and different years of salmon runs, like when they come in after so many years. And so one of the things they looked at, is it better to release a lot of sediment in one season and you have a huge impact on one year, but then not less on the other years, the other runs that come back? Or is it better to spread it out more, where maybe you have a intermediate impact on multiple years? And so that was all they were able to look at all that, using sediment transport modeling as a tool, like Stanford was talking about with the gates. How quickly do you open the gates, and how long do you leave them open, and how much do you open them? And that corresponds to, you can take down the dam in stages, where you lower it maybe a few meters, and then wait a season, and then lower it maybe another 10 meters and wait another season. So that's in Matilaha, and that there's some other things going on there with alkali concrete reaction stuff going on.
That's true.
That made it unsafe. But that's the same theory though.
Yeah, you can notch things gradually, and watching some of these case studies, which I'll add to that website. I'll add a bunch of these case studies for Elwha and some of the other major ones that have been done. And there are actually some very good documentaries that have been produced for the layperson. Not as technical as we're getting today, but about some of these issues. Marty, if you wanted to also comment, then as a user of multiple models, different models that can kind of perform some of these functions. Maybe if you could just discuss a little bit about the trade-offs between your uncertainties that you have in the input and in the variables versus the differences you might get in using other models. We've presented results from case studies using 2 different pieces of software here. Those are not the only ones. You'll be able to do some of these same things that we're talking about today with in TwoFlow and in other models that the Australian Water School also has offerings in. But they're all going to require similar input data and have similar uncertainties. So that kind of balance between the selection of model and what kind of uncertainties you get out of that versus the input variables and how much things might vary. Any comments on that, Marty?
Well, it's I have to say, HEC has great models, but all models have pros and cons. There's always trade-offs. Some are really good for some things and not so good for other things, and vice versa. So, it's really looking at the model and what the capabilities are and what it was designed for. There's one of the reasons that we used SRH2D for some of our projects is this ability to have multiple different subsurface layers and characterize those differently. They also handle the grids and the computational grids in different ways. With HEC-RAS has a subgrid bathymetry. Other models do things differently. So there's some trade-offs on how you characterize your system, and a lot of it comes down to the judgment of the modeler. And a lot of us have heard the saying, it's not really the model, it's the modeler, in terms of understanding the model and what its strengths and weaknesses are, and what the limitations are, because every model has limitations, right? So I don't think there's any one tool, in spite of some of the advertising I've seen, any one tool that can do everything really well. Different models do things differently, and it's up to the modeler to figure out, hey, what's going to be best for the questions that I need to answer.
Thanks. Yeah, and Stanford, if you want to comment on that as well, and then just wrap up any, maybe if you might have to consolidate some of the comments that have been made here. We'll try to address some of these separately. If there are any we didn't get to, we'll try to put those up with the additional resources. But because we're getting close to the end of time here, but wanted to give you the chance, Stanford, to just comment on any of the things that you've seen come up.
Yeah, I mean, I know most of the guys that are developing these sediment models, and they're all great. There aren't really sediment models out there I don't like. I can't throw, even if I wanted to, I can't throw shade on any of them. In fact, one of the things we did at a recent conference is I got four sediment model developers together, and we just talked about the principles of sediment modeling, and we actually agreed on almost everything. We're actually gonna run that in the podcast as a fun conversation. And so, I think the general principle is, develop your modeling skills, and then use as long as you're going to find that for many problems, there are models that are going to be too complex and models that are going to be too simple for the modeling question you want to answer. And your model selection has to be question driven. And so then you have this basket of models that will help you answer the question that you've been given. And then I would say, which model are you going to be the best modeler with? I think at that point it comes down to model comfort.
Yeah, no, thanks for that. So I sincerely appreciate Marty and Stanford, your time today. Thanks so much for coming on. I think this has been a valuable exercise. You'll see some additional resources come up here. Do join us on the Australian Water School's future webinars and courses, one of which we're going to talk about, and it gets to be kind of controversial given some of the loss of life and environmental damage from tailings dams. Analyzing those, there are some similar principles in trying to analyze what happens when a tailings dam fails, and some of that material goes downstream. And again, different models have different ways of dealing with changing viscosity and yield strength over time, and there are some pros and cons. In the end, though, the thing we need to recognize from the physics here is that a dam will reduce the sediment transport carrying capacity of the system. And that tends to drop out sediment, and downstream of that, you're going to increase its capacity. If you allow that same flow to go through with less of a load, then you're going to increase that and result in some scour. So those basic principles, no matter what model you choose, are going to have to be honored. Physics is physics. And so as long as we understand the underlying physics, we can hopefully do a better job of predicting these things and showing stakeholders what's going to happen, and that we do have a limited life for dams and reservoirs. So with that, we'll just do a quick closing remarks. We're about out of time here, but let's give both of you the chance to just give a closing remark, a take-home message, and then we'll close it off till next time. So let's go in the same order we went in for presentations. Marty, and then Stanford to wrap it up.
Sure. I'll be real quick, but I think one of the questions went along this too is like, well, what do you do with sediment and what's in your reservoir? And I know this is a message that you'll hear probably on the podcast with George Annandale, but we need to change the dynamic about how reservoirs are planned and make sure that they're designed to be sustainable, which wasn't the paradigm in the past. And so if anyone here is working on a new dam, consider sediment up front, consider the full cost of what it takes to manage. And, if removal is going to happen sometime in the future, include that with your overall cost. And so, we really need to be focused on sustainability. And I've talked to George about that quite a bit. And, I like to spread the same message that, the models are great tools that we can use to help examine different management options. And, that's one of their main uses. And that's what we use it for a lot. It's like, how can I manage my sediment better? How can I extend the useful life of my reservoir? So excellent. I'll leave it at that.
That's a great message. Stanford, bring it home for us.
Yeah, same thing. I'm involved in a lot of projects that have questions with only bad answers, right? Because we have been bequeathed a portfolio of reservoirs that did not think ahead about how the reservoir is going to be managed on the century scale. And we're involved a lot in Southeast Asia and South America where new dams are going in, and that's our message: is you need to give this gift to your grandkids so that this reservoir is still operational and has much less environmental cost. It's one of the places where economic sustainability and environmental sustainability actually are synergistic and work together if you can build it in at the beginning.
Yeah, thanks. And your message in the end, I mean, I think that's kind of the take-home message in all this, is scary. You said every dam will fail. Now, it may not fail catastrophically, it may not fail structurally, but it will fail to deliver the promised its promised capacity if we don't account for these things, and if we don't take other countermeasures to help it achieve its original purpose in a sustainable way. So with that, thanks so much for coming on. Thanks for your questions in the background. We will add some of the resources that have been suggested. I'll add those to that background website, hydroschool.org/mud. Do join us for some future courses. We're excited to bring this content to you. 100 countries from around the world joining us today. Attendees, almost 1,000 attendees. This is an excellent turnout, and it's a topic that I think warrants some further discussion. So fill out that survey at the end. Let us know what you want to see more of, and we look forward to seeing you again here with the Australian Water School. We'll see you next time.